When Laura asked me to put this seminar together, I wasn't exactly sure what I would cover because there's, well, literally hundreds of lectures and presentations that I've given over the years. But I thought it might be interesting to start off with a little bit of Alberta context, a little bit of history of lidar and application domains, and then look at the latest and greatest multi-spectral lidar, which we now have in our lab here at the University of Lethbridge. So this is essentially a two-part presentation, and both parts are essentially recycled from earlier talks. The first part is one that I was invited to give to a number of delegates from Alberta Innovates and a couple of assistant deputy ministers for Alberta. They wanted some context on LiDAR and environmental monitoring. So at least the first part is in the Alberta context specifically. And then the second part is a presentation I gave to a NASA working group a few weeks ago, which was on all different flavors of LiDAR, latest and greatest, where LiDAR is going, and I was asked to talk on multispectral. So the second part is quite fresh in my mind. The first part is not very fresh in my mind because it's from a couple of years ago. So hopefully I can remember what that was meant to be about. Okay, so we'll start with Alberta just to bring this to a context that we all understand. As we all know, the historical context for resources and economy is that Alberta's economy is very much dependent on oil, natural gas, coal, and minerals, or has been historically. That's been a big part of our economy. Moving forwards, of course, we're aware that Alberta is also very wealthy, very rich and abundant renewable resources, and so this is probably part of the future context for Alberta, something that we need to pay attention to, and we do expect growth in that area. Now, so that means we have bountiful natural capital in Alberta. We're lucky as a province in that regard. And what I mean by natural capital are the assets, natural and otherwise, of the Rockies, the prairies, forests, and wetlands. And so in order for our province to reap the maximum benefit from these resources, we need to apply stewardship, sound stewardship, environmental monitoring, and high quality spatial monitoring. Spatial data is required. Now, the reason for spatial, of course, is because the natural capital exists across the land. And so space is very important. I'm a chair in remote sensing, so of course I'm biased in that I believe remote sensing is part of the solution for that. Now, threats to Alberta's environments are, of course, or threats to Alberta's advantage is, of course, an economic over-reliance on dying natural resources, many of those that are deeply buried in the ground, slow development of ubiquitous renewable resource industries, and there is an increasing threat of natural and anthropogenic hazards, such as wildfire, floods, drought, severe weather, and transportation spills. And so there's a few examples listed there from recent history. And sometimes it seems like we see more and more hazards and natural disaster events in the media. Now, all of these threats and opportunities are spatial, but as is the tendency with hazards, the timing is indeterminate. So let's look at a couple of examples. So floodplain hazards, for example, floods tend to be restricted in spatial extent. So we have a good idea where floods are going to happen, but not necessarily when. And, of course, floods tend to happen in low-lying ground. Now, drought is also a real hazard in Alberta, particularly here in southern Alberta, where we have a high reliance on agriculture. But that's less spatially deterministic. Although, of course, again, upland areas tend to be more at risk of loss of water through drought due to diminished water tables. And then, of course, wildfires. That's very prevalent today, especially if you look at what's going on in the western United States right now. And anyway, but fire hazards tend to be restricted to forested areas or areas where there's a lot of fuel. So there's some difference in where these hazards manifest themselves, but there's one element that's common to all of them, and that is that these are essentially 3D phenomena. They happen in space, but there's a three-dimensional element to these. And so in order to understand these hazards and potentially implement mitigation strategies, we need to start thinking in 3 dimensions. And so that brings us to the topic of today's presentation. and that is lidar. And so the title that I outlined at the beginning was LED to lidar, I think. Anyway, so in our lab here at the University of Lethbridge, we work with various flavors of lidar, from very low-powered LED systems, which provide very short-range measurements, to high-altitude airborne lidar systems. And we also have a couple of terrestrial laser scanners as well that we mount on tripods, and they can monitor at the plot scale up to a few hundred meters away from the sensor. But I won't be talking about those today. We'll just look briefly at LED and airborne lidar. Now, airborne lidar really found its niche a little over 20 years ago with floodplain hazard assessments. Up until that time, land survey techniques had been the norm for surveying flood hazards. Of course, the requirement is to understand the terrain within a floodplain environment so that we can map inundation, and so that we can run hydraulic models to assess floodplain risk. When airborne lidar came about, that enabled very, very rapid and reasonably high accuracy assessment in a fairly short period of time over fairly large areas. I think of an example back in 2000. I was part of a mapping project where we started in one corner of the state of Arkansas and mapped all the way down to the other corner on the Mississippi and various tributary floodplains. And at the time, that was the largest ever floodplain mapping exercise. And that project led to a proliferation of other flood insurance program mapping exercises in the US. And so really that's when LiDAR came to fruition as a commercially viable tool in this application domain. So of course, what it allows us to do is to map high resolution across the floodplain, and then we can use that to predict water levels under various discharge scenarios. And so here's the old man. There we are. Oh, that's where we should be, in that building over there. Anyway, so here's the LiDAR imagery or 3D imagery of the floodplain. And then we can ramp water levels, run hydraulic models, and develop these kind of standard flood risk hazard maps. So that's kind of a staple of LiDAR. It's a very well known, very well developed application area now. Nothing new or fancy. I wouldn't say this is research, but it's really where LiDAR got its first foothold, or airborne LiDAR. Now, moving on, this is more future oriented. We're currently in the process of integrating LiDAR with other tools to bringing into the move from the hazards into water resource monitoring. And so what we have as an example here is we can see a LiDAR DEM background, and then the time series that you see here is actually a radar image set or image stack of water extent. Now we can also use optical data for that, but anyway, there's lots of different satellite sources that can map water, and so then you can transpose or overlay the water image sequence onto the DEM and develop a hydro period, and you can utilize the LiDAR for quality control as well. And then from the two, you can extract a time series of inferred water levels or water depths. So these are not mainstream applications at the moment, but this is kind of where we're at. So I've illustrated the start of LiDAR for water-based flood risk assessment, and this is kind of where we're at today, is the fusion of LiDAR with other technologies for water resource monitoring. Another application in the water resources domain that we're currently pioneering at the University of Lethbridge is Snowpack mapping. Now, interestingly, NASA JPL in the US are also working in this domain. So I'd say for them, it's perhaps a little bit more operational. They have slightly better resources and deeper pockets than we do at the University of Lethbridge. But, you know, it's kind of cool that we're working on some of the same projects that NASA are. And our work, of course, is supported by the government of Alberta, because headwater snowpack is a critical element of our water resource here in southern Alberta. So there's a good rationale for that, and we're making a lot of headway with developing these applications. So moving down in scale, but sticking with snowpack in the headwaters, This is where we've pioneered development of LED ranging technologies to map through time. So as you can see here, this is through time. And what we've got here is a cross-section or a profile across the ground of snow depth. So you can see the variation snow depth through time and across space. Now that's only a few meters in space, but the innovation here is it's actually given us a 3D representation of the snowpack surface, and we're monitoring that continuously. So that's not something that, well, that can be done, but historically that's a rather expensive thing to do. What we've been able to do is do this with fairly low cost, you know, $1,000 to $2,000 of instrumentation with very low power. So here you can see the little LED sensor mounted on a tower, and that can be powered from batteries and a solar power, just like regular environmental instrumentation. So it doesn't need mains power supply. So anyway, that's an innovation we're working on as well. So two different scales, in situ LED and watershed-based airborne LiDAR. Now, moving to forests, but sticking with the LED technologies, another one of my grad students, this is work by Celeste Barnes. I should remember to acknowledge all of my grad students. This is another recent PhD student, Zhao. He developed a little robotic scanner with the same LED ranging technology, but he modified it so that it would rotate and scan around itself. And by integrating with a little camera, he could capture simultaneous images and LED-based ranges, and then fuse all of this information to develop a 3D representation of the tree canopy surrounding it. And so this is what one of the LED images looks like. And then this is what it would look like after you've extracted an individual tree. So we can do a lot better with high cost, highly sophisticated ground-based laser scanners, of course, but those instruments cost tens to hundreds of thousands of dollars. Again, here we're talking about a few $100 to $1,000 LED system with a few $100 worth of peripheral devices and a Raspberry Pi to pull it all together. So we could probably build that and sell it for $2,000 or $3,000. And even though it's not as accurate as a high-cost terrestrial laser scanner, the beauty of this is it could probably be left in situ for monitoring. So this kind of technology has application in time series monitoring of maybe canopy phenology or changes in the leaf cover. So that's something we're trying to develop in the lab as well. Now, again, moving back up in scale to the airborne LiDAR domain, here I'm illustrating forest canopy models. This is in kind of north-central Alberta, in the Slave Lake area. And this is just a canopy model. So in itself, not particularly exciting. That's a very easy derivative to extract from a LiDAR point cloud. This is over 5 to 10 kilometer range, 1 meter canopy height model. Okay, not that exciting. But the neat thing is we've been able to capture this data over many years. And actually since this 2016 imagery, we've got 2 more data collections, which I don't illustrate here. But if you look closely, you can see the color ramp changes. Forgive me, I don't have the color ramp here, but greens to blues represent the tallest canopy elements. And so if you kind of focus on one area in particular, you can gradually see that the canopy is actually getting taller. And so if we subtract the first and last image, what we can see is canopy growth over that time. So red represents loss, and then the kind of yellows to browns to greens to blues represent growth. This is the influence of a wildfire. And so across this landscape, we can see different patterns of growth. Interestingly, this is showing us that there is forest encroachment into the wetlands. And we've got some areas of wetlands that have completely dried out and have now completely filled over with forest cover. Now, this is interesting because this 14-year time series is illustrating for us a lot of the environmental processes that are occurring in that landscape. And in effect, what we're seeing is the impact of landscape drying. Now, we could also utilize optical imagery for this, but optical imagery would not be able to show us the rate or the amount of growth that is occurring in these areas. And maybe a couple of, this is one interesting area I'd like to highlight is here we can see some loss of canopy. And if this was an open forum discussion, I'd probably ask you what that was, but I'll tell you that's actually the influence of beavers. So that's kind of a fun observation. Now, I'm just going to zoom in a little bit and then show you another image. What we have here is a classification of those change processes. Now, this image is just a subtraction. So that's interesting in itself, and that tells us a lot. What we have here is a classification using the entire image stack and then doing a trend analysis on each pixel. And so from that trend analysis, we can then do a supervised classification of these different types of change or disturbance. And so just to illustrate what the trend analysis looks like, here we can extract different linear or power function or polynomial changes for each one of those pixels through time. So a linear change would just be, you know, there's everything's changing gradually. You can imagine like a canopy height is increasing, you know, maybe at a rate of 50 centimeters per year. Power function might represent, say, the canopy is starting to accelerate in its growth through time. So maybe in the first couple of years, it's growing at 50 centimeters, but then in the latter part of the time series, it's growing at, say, 1 meter per year. So that's where we see a differential rate of change. And then in this case, we've got a quadratic function or a polynomial quadratic. Now in this case, we might see a decline to begin with, and then an advance. So one example of that might be a disturbance event where the forest dies or wetland ecosystem dries out, and then that's followed by growth, maybe as the ecosystem transitions from one form to another. And so anyway, so we're also trying to pioneer these different types of landscape classification using 3D LiDAR data via trend analysis. So we've got some interesting research going on there. Slightly more simple, but perhaps more practical in application, we've been developing growth curves from time series LiDAR. So here we can see a chronosequence of different forest stands. What I mean by a chronosequence is that they have different ages. So here we've got a forest that was, or a forest stand that was clear cut in 1994. Here a clear cut from 2002, here from 1975, and here's a very old one where there's a wildfire in 1918. So each of these forest stands was kind of raised to the ground at a different point in time, and then they've been allowed to naturally regenerate or recover. So that's what we mean by chronosequence. And we actually have multiple LiDAR data sets captured over these sites. Here we only see from 05, 08, and 11, but we also have 2015 and 2019, and maybe 2021 if we get out there again next year. So we've got multiple points in time over this chronosequence. So this allows us to populate a growth curve of biomass. So we can convert point cloud information, that kind of three-dimensional structural information of the canopy, into an estimate of biomass using plots to calibrate it. And so we've done that work, and then this allows us to develop this growth curve. And so I'm not sure if you're familiar with the concepts of population growth, maybe from human geography you are, but standard growth follows a logistic function or a sigmoid curve. So you see growth tends to start slowly at first, then it starts to become kind of exponential. And then once you reach some level of maturity where resource consumption starts to be limited by available resources, then you start to see a drop-off or a more logarithmic characteristic to the curve. So this is a standard growth curve, and most ecosystems and biomass conform to this kind of growth curve. And so we've been able to populate that using LiDAR data. And so we're now in the process in my lab of developing these kind of techniques across many landscapes in Canada. And that has real application, particularly for forest resources, and even just understanding ecosystem dynamics and carbon accounting, for example. Now, just a couple more examples of change. I now have 20 years of data over Peyto and the Wapta ice fields, but this just represents a 10-year time series. And so you can see the change in morphology of this Peyto glacier. and the down wasting. So we got up to 40 meters of down wasting over that 10 years, probably at least double that by now. And then on the image at left, you can see, oh, sorry, I got to do this again now. Well, these are kind of fun animations, so why not look at them again? Then the image at left, here we're watching the seasonal phenology in leaf area index over a forested canopy. So these are just illustrations of how three-dimensional LiDAR data can be utilized to track changes in morphology and ecosystem biomass. So hopefully, well, I'm coming to the end of part one. Hopefully this illustrates that LiDAR is a useful tool for enhanced environmental monitoring. It observes 3D attributes, but when you have a sequence of images, that gives us four-dimensional change or the cumulative impacts on the landscape. And so that allows us to devise new analytical techniques. And so that's something that my lab is specializing on right now, is these new analytical techniques to extract 4 and possibly even 5-dimensional information when you look at differential rates of change. One of the beauties of LiDAR in general is that the technology can be implemented over multiple scales. As you've seen with the LED technology, it's very kind of small scale in situ. Terrestrial or ground-based scanning systems, which I haven't illustrated here, are very good for plot level extractions. So here we can see some individual tree stems and branches and foliage information very accurately represented from terrestrial laser scanners. Then we can move to the landscape scale. So this is the bread and butter of our airborne LiDAR system. And now we can move to more even continental or global scale, utilizing satellite LiDAR systems. So there was one for the longest time, that was ISAT-1, that was decommissioned a few years ago. ISAT-2 was deployed last year. And then there's one other one, JEDI, that's on the International Space Station. But that doesn't really operate in Canada. That's only up to, I think, about the 50th parallel. So anyway, right now there's one mainstream satellite LiDAR system, that's ISAT-2. And so anyway, utilizing these different LiDAR systems, we can fuse the data, integrate cross scales, and go from plot essentially to global scale. So there's some interesting scaling up opportunities there. The airborne and the ground-based technologies are becoming cost-effective for monitoring. Satellite has the potential, but isn't quite there yet because the routines haven't been developed, but that'll be coming online soon, I imagine. And of course, the new kid on the block is new multi-spectral technology. And so that can do most of, well, everything we've just described, but it also has bathymetric capabilities and spectral capabilities. So that's kind of a new paradigm in dealing with LiDAR technology. So that's going to be the next part of my presentation. So now we're kind of moving forwards to the talk I gave a couple of weeks ago. So what I'd like to present here is basically a number of case studies that we've worked on in the last 3 or 4 years utilizing multispectral LiDAR. Now my lab has only had this technology for a little over a year now, but we have been working with the manufacturer since 2015, and we've been able to gain access to the sensor on a periodic basis here and there, and so that has allowed us to do a number of studies. Now, the difference with the multispectral LiDAR, or the Titan system, to normal airborne LiDAR systems is that it operates in 3 wavelengths. So you can see here we've got a 532 nanometer channel, so that's in the green, in the visible part of the spectrum. And then we've also got a 1064, which is just on the edge of the near infrared, so that's outside of the visible. And then we also have 1550 nanometers, which is more in the shortwave infrared range. And so you can see how that matches up to Landsat bands. So we're close to band 2, close to band 4, and close to band 5. So anything we can do with those bands in an optical sense, we should be able to do with the multispectral LiDAR as well. So that's one of the things that we're testing. And so here you can see also the spectral response of different land cover types. So water down here, vegetation and soils. Any of you that are doing other remote sensing courses appreciate that different land covers, of course, have different spectral properties. And so that's one of the things we're trying to capitalize upon with the multispectral capabilities. So here we can see standard DEM terrain information, fairly standard LiDAR canopy information, but now we're able to generate imagery. colorized spectral imagery, things that look like photographs, something we couldn't really do with LiDAR in the past other than in a black and white sense. Now we can kind of colorize these images. So this is an intensity composite. A little bit of information on the technology itself. So here's the wavelengths I've just mentioned. One of the differences with each one of these channels or wavelengths is that they have a different look angle. And the reason for that is to avoid interference between the channels as they're traveling through the optical path on the sensor. So the nadir channel is channel 2, that's 1064 nanometers. And 1064 has historically been a very standard wavelength for airborne LiDAR systems. So this is useful because what that means is channel 2 alone is quite comparable with historical LiDAR datasets or data collected from other sensors. Channel 1, the shortwave infrared channel, is angled very slightly forwards. And then channel 3, the green channel, is angled at 7 degrees forwards. Now, there's another reason for this angling forwards, and it's not just about avoiding interference. It's also because when you angle it forwards, you're not likely to get spectral reflection. When you shine a torch at a mirror, hold it at head level, shine it at the mirror, it's going to blind you, right? The light's going to come straight back at you because of specular reflection. So the idea of angling it forward is to avoid specular reflection. And the benefit of doing that is it actually means you've got a reduced range in the intensity or the signal strength response. And that has some benefits, especially because the 532 channel is a bathymetric channel. And so we need to get penetration into the water. If we angled it at nadir, we'd probably lose some of that signal because of the high dynamic range in the spectral response. Anyway, we're probably delving too deeply into technological elements here, but happy to talk about that later if anyone has any questions on that. Is the rep rates, beam divergences also vary slightly. Now, one of the reasons for channel 3 having a larger beam divergence, what that means is a larger footprint on the ground, is because it's visible. And if you were underneath the laser when it flew over, that's a dangerous wavelength to have shining in your eye. I mean, it could blind you. So one way to mitigate the danger from that is just to spread that energy over a larger footprint. And so that's why 532 is larger. It also helps with the bathymetric attributes or requirements in that channel. Again, differential pulse energies and pulse width. So some of the technicalities there that we don't need to delve deeply into. Okay, so one of the staple applications of the Titan system is its ability to do bathymetry. Now, it is not exclusively a bathymetric mapping system. There are other laser systems that are exclusively optimized for bathymetry, and they're more sophisticated, more complicated, bigger, more expensive. And the Titan isn't one of those. The Titan is not a dedicated bathymetric mapping system. It is intended to be a near-shore bathymetric mapping system combined with the regular kind of terrestrial mapping applications that every other regular LiDAR system can do. So it's a multi-purpose system. And so this just illustrates cross-section through a floodplain. So we've got our vegetation information, we've got our terrain information, and we've got some river bathymetry. So you see the water surface and the riverbed. And so this is that landscape. This is an optical image. Incidentally, optical imagery is also captured with the Titan, so we've got a high resolution camera on board. And then here's our water depths beneath that water surface. So that's the kind of standard bathymetric product that the system can deliver. The more typical products, of course, DEM, DSM, digital surface model, and CHM, canopy height model. So these are the kind of typical geometric derivatives that we get from the Titan, just like any other airborne LiDAR system. But here's where it starts to get interesting. We can extract an intensity channel, or kind of like almost a signal reflectance, but it's not true reflectance, but it's an index of reflectance. So we have an intensity image in each one of the channels. And then if we combine those as a composite image, we can develop a colorized composite that looks something like a photograph. And then just to kind of merged these two data sets. So we've got the colorized composite and we've got the 3D geometric model. And hopefully this is a landscape that many of you recognized. Here we have the Icefields Parkway, here we have Bow Lake, and here we have the Wapta Icefields. So if any of you have been to Banff National Park recently, you've probably seen these mountains. And I've been flying these mountains for 20 years now. We have, I think, 7 or 8 data sets over here. And so incidentally, I'm looking for grad students who would like to work with this data set and do some interesting glacial dynamics and classification work. Just a heads up. Here again, we have another one of these composites, and it's draped over the hillshade. So you could argue there's also 3-dimensional information here. So this is 3D plus composite. This is a permafrost landscape in the Northwest Territories. So here we can see permafrost plateaus, we can see a fen, we've got some upland forests. Anyway, that might not be an intuitive landscape for many of you to look at, but the neat thing is now combining the 3D and combining the spectral, we can do some neat kind of classification work with that image that we couldn't previously do. So, you know, we can do things with this that we can't do with optical imagery and that we can't do with regular LiDAR imagery. So it's kind of a bit of a paradigm shift in remote sensing. Okay, so let's look at some of the recent case studies from the lab. Maxim Okremenko, a recent master's student in my lab, was looking at the spectral reflectance properties, essentially trying to convert the laser signal intensity into a spectral reflectance. And so that requires some radiometric work. Here you can see the intensities from each of the channels. Here we've got some targets which were surveyed in, and we've also used Craig Coburn's in goniometer to get the reflectance over these surfaces. And so anyway, so we can do some fairly hardcore laser intensity calibration, and that allows us to develop new products. So some of the products we work trying to develop are normalized ratios, things like shortwave infrared to near infrared, which is analogous to a burn ratio in the optical community, and then visible to near infrared, which is analogous to a normalized difference vegetation index, something that we're all probably quite familiar with. So here you can see the signal intensity response in each one of the channels. Now these are calibrated and normalized by the manufacturer, so we can't really do much with these intensity histograms ourselves other than to calibrate them to reflectance. And so that's what this allows us to do. So using reflectance targets, we can now convert this into an actual reflectance. But another thing we have to be aware of with the LiDAR, which is different to a satellite sensor, is that the signal response property is going to change with altitude, right? Because we have a high rate of laser signal attenuation through the atmosphere. So as we fly higher and higher, more of our signal will be lost. So this is analogous to atmospheric correction in optical imagery, because of course, as we fly higher and higher, there's more atmosphere to correct through. So the path length increases. And so you can see the influence of that here in this normalized difference vegetation index image set, which was flown at 500 meters to 1,000 meters to 1,500 meters. So we've got, with a 500 meter increment in flying altitude, we actually see quite a difference in the high vegetation cover areas. And it's not so much that the signal changes, it's more that we actually lose a lot of our visible signal. It's just completely attenuated or lost by the time we get up to 1,500 meters. So these are also some of the things we're trying to understand and account for. Now, with regular airborne LiDAR, we can develop 3-dimensional foliage information, and from that we can extract 2-dimensional vertical profiles. Now, what I'm illustrating here on left is that these profiles differ in each of the channels. So here we can see a profile, the vertical cumulative distribution profile of the point cloud for 3 different forest cover classes, so mixed, conifer, and hardwood. And then here we can see the deviations from that normal curve in each of the channels. So here, green minus near infrared, and then here, shortwave infrared minus near infrared. So what this tells us is that we've got a big difference up to a couple of meters or so for different increments in that profile based on the channel that is used to develop the profile. Now, that's useful because what it tells us is that each one of these channels samples that vertical foliage profile differently. So each channel gives us different information about the canopy structure. It also gives us different intensity, different spectral information. So we can capitalize on that different structural information and different spectral information to develop new products. And so this is one of the things we're trying to pioneer in the lab, is the utilization of new vertical profile indices. So these are spectral profiles through the canopy. And here you can see a voxelized representation, both of the structural information in the canopy, but also combining the normalized ratio information or spectral information. So this represents spectral and structural information in one cross section. So we're basically developing entirely new data structures. And what we do with them, we don't really know, because there's no standard ways to work with these data structures. So some real opportunities for some innovation and creativity and paradigm shifting research here. Now back to more mundane optical type classification, or new opportunities that we can very easily understand. Here we've got some spectral signatures for different land cover classes of sand, asphalt, gravel, larch, conifers, hardwoods, hay, corn, right? So number of land covers. Here we've got a regular image composite, so that 3-channel laser intensity composite. And then using these channels, we can do a supervised classification. Real simple maximum likelihood supervised classifications, or something that we all understand. We can do this in ArcGIS. We don't even need sophisticated remote sensing software for this. And so using this fairly rudimentary classification approach, we can now extract these land covers at a fairly high resolution, say a 5-meter pixel resolution. And that's just from the multispectral LiDAR intensity image. Now, ramping it up a little bit, going to a slightly more sophisticated level, now what we can do is we can extract individual clusters of common intensity and structural attributes. So essentially, we're combining the intensity information from the last slide, but now adding in structural indices. I don't want to get into detail on what those structural indices are, but they're representatives of the foliage profile. We're just pulling out statistical indices of the foliage profile, combining it with the intensity spectral information, and then clustering areas within this forested landscape into zones of common clusters, and then applying the classification. And so that we can even get down to individual tree crowns if they're large enough. And so that is allowing us to now classify species. So not just land covers, now we can get down to species and potentially even at individual tree level. So a paper was published on that in 2017, and many people are now working on that type of combined spectral and structural classification. So that's kind of where the research is at right now. There's a lot of research going on in that area. One of my colleagues at the University of Calgary worked with us actually just over the last year to look at ground level or understory level classifications by combining the multispectral LiDAR with optical image products and an object-oriented classification approach. So the object-oriented approach pulls out features, and then combining the optical and the multispectral and the structural information, kind of a statistical machine learning approach was used to map out coarse woody debris. So again, we're looking right at ground level now. So this is the kind of thing you would not be able to do with optical imagery. It can only be done with something that samples at the ground level through the canopy. So that requires LiDAR. But the beauty here is we're integrating the spectral information to try and classify those features at the ground level. And so coarse woody debris is basically being the first thing that anyone has looked at. Moving forwards, I'm sure we'll start to classify ground level products across a range of application areas. But this is the first of its kind for that kind of classification. So that's kind of neat. Now here's some of Laura's work. Obviously Laura could speak better to this than I could. But one thing we were able to demonstrate was that LiDAR, not just multispectral LiDAR, but any airborne LiDAR, if it's well calibrated and you have pre and post fire in a peatland environment, you can potentially map depth, burn depth. As most of you probably know, a wildfire over a peatland landscape, that organic carbon-rich peatland mat is going to burn down. And so burn depth is something that's of interest. LiDAR can map that. It's pretty noisy in some places. It's not a nice, smooth measure of depth, but at least it's better than any other measure of depth. And then when we integrate the near infrared and shortwave infrared, we can develop what's known as a normalized burn ratio. And so I don't think I have it here. Laura probably does somewhere, where we've got an image of a satellite-based normalized burn ratio, and that is an index of burn severity. What we've shown is that utilizing the multi-spectral LiDAR, we can also pull out a normalized burn ratio. And just visually, you can see that this normalized burn ratio, red being an index of severe burn, spatially correlates with the areas of burn depth over the peatland. And so this burn ratio appears to be a good index of burn depth or burn severity in that kind of landscape. So lots of potential for utilizing the 3D and the spectral information for wildfire burn assessments, both in canopy and in peatland environments. Oh, wow. Okay, so we'll come to an end. That was a rather quick fizzle. Sorry. Anyway, here's the case studies that we've examined. I really should have thought of a wrap-up slide for this. But anyway, I guess in summary, what I could say is that multispectral LiDAR has opened up new paradigms in remote sensing, largely because of the integration of spectral and structural information. And there are still many opportunities for new research. In my lab, we're focused primarily on change, ecosystem change. And so we're utilizing multispectral LiDAR and historical LiDAR for those. But we're also working on the technical end of developing these or exploiting these new paradigm opportunities. So thanks for your time, and very happy to take some questions.